Hi. We're conducting a poll for Project Mathematics. What can you tell me about the number pi?
Pi? Well, it's sort of like 22/7, but not exactly.
It's 3.14 something, I think.
Well, doesn't it have to do with the area of a circle?
It's the circumference of a circle. No, it's diameter. No, it's the circumference of a circle.
Pi is the ratio between the diameter and the radius. Wait, that can't be right.
Pi is the magic number for circles.
Obviously, if you want to learn the meaning of pi, you can't do it by conducting a poll. Here's an experiment you can do by yourself to discover what pi is. Measure the circumference of a circle and divide by the diameter. The ratio of the two lengths is always the same, no matter what size circle you use. This constant ratio is called pi, the first letter in the Greek word for perimeter. Its value is between 3 and 3 1/7. This program deals with two important questions. First, how do we know that the ratio of the circumference to the diameter is the same for every circle, whether it's small, the size of a coin, or huge like the sun? Second question, how can we determine the exact numerical value of pi? We'll also see why people have been fascinated by this number from ancient times to the present day.
Whenever you see a circular object, the number pi is always there. For example, look at this circular disk. Its circumference is 2 pi r, and its area is pi r squared. The disk can be moved to sweep out a solid cylinder whose volume and surface area involve pi. A rotating right triangle sweeps out a solid cone. Again, volume and surface area involve pi. The same is true for a rotating semicircular disk that sweeps out a solid sphere. And if you look at formulas for the volume and surface area of a donut-shaped solid called a torus, you'll find pi squared.
Pi crops up in the length of the shortest airline route from New York to Tokyo, and also in the formula for the time it takes a planet to make an orbit around the sun. But what is more remarkable, pi is found in many fields that have nothing to do with circles. For example, balls falling at random into slots at the bottom of this apparatus will show a pattern much like part of a bell-shaped curve called a Gaussian curve. Some school teachers use Gaussian curves to assign grades. Calculus students learn that the area of the region under this Gaussian curve is equal to the square root of pi. Electrical engineers find pi in formulas related to alternating currents and radiation from radio and TV antennas. Formulas from calculus show that pi has remarkable connections with the integers. There are infinite sums of reciprocals of integers that add up to expressions involving pi or pi squared. There are infinite products of ratios of integers that yield the value pi. Wherever you turn in mathematics, from trigonometry to advanced calculus, you're likely to meet pi. Long before the invention of the wheel, early man identified the circle as a powerful symbol in nature with infinite symmetry. To build circular stockades or circular temples, people needed to estimate the total distance around in terms of the total distance across. Early civilizations realized that the ratio of circumference to diameter is the same for all circles. And by careful measurement, they found that this ratio was a little larger than 3. The Babylonians used the value 3 1/8, or 3.125. The Egyptian value was slightly different, 256 divided by 81, or 3.16. An approximation to pi also appears in the Bible. The Old Testament describes a circular basin in Solomon's temple, 10 cubits across and 30 cubits around. These rough estimates give a ratio equal to 3, a bit low. Although many people realize that the ratio of circumference to diameter is the same for all circles, the Greeks were the first to explain why. It's a property of similar figures. As we saw earlier, if you start with any circle and expand or contract it by a scaling factor, you get another circle. And the circumference changes by the same factor. So, the ratio of circumference to diameter is the same for all circles. Small or large, on Earth or in the heavens. This constant ratio, which we call pi, is a fundamental constant of nature. It enables us to find the circumference of any circle in terms of its radius. The circumference equals 2 pi r. Another ratio that's the same for all circles is the area of a circular disk divided by the square of its radius. Again, similarity explains why. Start with a circular disk of radius 1. If you expand or contract it by a scaling factor, its area is multiplied by the square of the scaling factor. Therefore, the ratio of the area to the square of the radius is the same for all circles. So this ratio is another fundamental constant of nature. More than 22 centuries ago, Archimedes, the greatest mathematician of ancient times, made the remarkable discovery that this constant is exactly equal to our old friend pi. In a moment, we'll see why. Stated another way, the area of a circular disk of radius r is equal to pi r squared. This important formula was rediscovered again and again in many different cultures. This drawing shows how the Japanese did it in the 17th century. Divide the disk into an even number of equal slices. Rearrange half of them like a row of teeth. Fill in the open spaces with the other half like another row of teeth. The new figure is almost a parallelogram, with the same area as the disk. If we repeat the process with smaller and smaller slices, the curved sides of the teeth eventually become more and more like a straight line, and the parallelogram becomes more and more like a rectangle, with base pi r and altitude r. So we see that the area of the disk is equal to pi r squared, the same result found by Archimedes. Here's another method. Divide the disk into equally spaced concentric rings. Form a rectangular strip with the same area as the outer ring. Its base is nearly equal to the circumference of the circle. Do the same with the other rings and pile them up. You get a figure that looks somewhat like a right triangle. The base of the triangle is nearly 2 pi r, and the altitude is equal to r. If you repeat the process, using more and more rings, the stack of rectangular strips looks more and more like a right triangle. So we have found another way to see why the area of the disk is equal to pi r squared. Because pi is so fundamental, people have tried for centuries to determine its numerical value accurately. The first serious attempt was made by Archimedes. He obtained approximate values of pi by using regular polygons inside and outside a circle. When we compare the perimeter of this inner hexagon with the circumference of the circle, we find that pi is greater than 3. The inner hexagon can be expanded by the scaling factor 2/3 the square root of 3 to form this outer hexagon, tangent to the circle. Compare perimeters again, and we find that pi is less than 2 times the square root of 3. Archimedes kept doubling the number of sides until he reached a polygon with 96 sides. And found an estimate for pi correct to 2 decimal places. The upper bound, 22/7, is still used today as a fairly good approximation for pi. For centuries, people in Egypt, India, China, and other cultures refined the method of Archimedes by taking larger and larger doublings. An incredible Chinese calculation with a polygon of more than 3,000 sides gave 5 decimals of pi. The Chinese also found a simple fraction, 355 divided by 113, that gives 6 decimals of pi. They held the world's record for more than 1,000 years until the use of Arabic numerals provided more efficient ways of doing arithmetic. When infinite series and trigonometric functions became widely known, formulas were discovered that made it possible to approximate pi without geometric diagrams. By the end of the 19th century, these formulas were used to calculate pi to hundreds of decimal places. In the 20th century, high-speed electronic computers were coupled with new mathematical methods that enabled computers to do arithmetic with very long numbers. More than 1 billion decimals of pi were known in 1989, and plans were made to extend the calculation even further. Why go to the trouble and expense of hooking up giant supercomputers to calculate 1 billion decimals of pi? One reason is to test the architecture of supercomputers. Calculating the first 1 million digits of pi is a good measure of the computer's overall efficiency. The calculation also helps check software and programs for speed and accuracy. Also, we can find out more about pi itself. For a long time, people wondered if pi was an exact fraction, like 22/7. A ratio of 2 integers, called a rational number, always has repeating patterns in its decimal form. For example, in the decimal version of 22/7, the block of 6 digits, 1, 4, 2, 8, 5, 7, is repeated indefinitely. As people calculated more and more decimals for pi, they searched for patterns that repeat over and over. But none were found. Finally, in the 18th century, it was shown that none would ever be found. The German mathematician Johann Lambert used continued fractions to prove that there are no integers whose ratio is equal to pi. Nevertheless, rational approximations are quite useful. The Archimedes approximations are closer to pi than any other fraction with denominator less than 100. And the Chinese estimate, 355 over 113, is closer to pi than any other fraction with denominator less than 16,000.
Here's another place where pi shows up unexpectedly. Cover the plane with square tiles. The vertices of the squares are called lattice points. Choose a convenient lattice point as the origin. Now pick another lattice point and draw the line segment between them. If no other lattice point lies on this segment, we put a bright dot there. All the lattice points behind this dot are hidden, and we mark them with dark dots. Now do this for all the lattice points. You end up with a symmetrical pattern. Another way of thinking of this is to say there are bright dots at all lattice points that are visible from the origin. If you go back and look at the pattern, you'll find that about 60% of the lattice points are visible from the origin. As this square expands to cover the whole plane, the fraction of visible points approaches the limiting value 6 over pi squared. This surprising result is often described by saying that a lattice point chosen at random has a probability 6 over pi squared of being visible from the origin.
But it also shows up in some problems where there are no circles at all. For example, drop a needle on a floor whose boards are twice as wide as the needle length. The needle might land on a line, or it might not. Drop lots of needles. The probability that a needle crosses a line is 1 over pi. Now what can you tell me about the number pi?
Pi is the ratio of the circumference to the diameter of any circle.
Pi is the area of a unit circular disk.
Pi squared over 6 is the sum of the reciprocals of the squares of all positive integers.
6 over pi squared is the probability that a lattice point chosen at random will be visible from the origin.
And pi is the square of the area of the region under a Gaussian curve.
Advances in the computation of pi have been markers of significant progress in the history of mathematics. Archimedes gave the first known proof concerning the value of pi when he compared perimeters of polygons inside and outside a circle. He showed that pi, like any number, can be approximated to any degree of accuracy by rational numbers. His estimate of 22/7 was improved 700 years later by the Chinese value 355 over 113, which gives pi correct to 6 decimals. Better rational approximations to pi accompanied major advances in mathematics, such as the adoption of Arabic numerals and decimal notation, the use of infinite series, the methods of calculus, and new methods developed in the 20th century to exploit the technology of supercomputers. People have calculated more than 1 billion digits of pi because of the human desire to do something that's never been done before. It's a challenge to the human spirit, like climbing a mountain or traveling to the outer planets. When George Mallory was asked why he wanted to climb Mount Everest, he replied, "Because it's there." Well, pi is certainly there. Like the outer planets, it's built into the fabric of our physical universe, and it will always be explored.